Hello, students, and welcome to the virtual classroom again. Today, we're going to talk about a specific type of energy. We're going to talk about nuclear energy. And there are two types of reactions that provide nuclear energy. Remember, nuclear energy is the energy stored inside the atom. So we're going to talk about fusion, which is when you fuse two particles or atoms together. And we're going to talk about fission, when you split them apart. Both of these reactions, fission and fusion, release an abundance of energy. So the first one to talk about is fusion. It's used in modern nuclear weapons. It needs heat and pressure from a fission explosion first to fuel it. And what it involves is two lightweight particles. So here we have our lightweight particles. Now we haven't done our chemistry unit yet for Science 10, but hopefully you remember from Science 9 that each atom has a certain mass. It's an atomic mass made up of its protons and neutrons. So when I say lightweight nuclei, I'm talking about ones that have not very many protons or neutrons in it. And it must be lighter than iron for this to happen. Iron seems to be just a little too much protons and neutrons inside the nucleus to allow for this type of reaction to occur. So it must be lighter. And that's Fe on your periodic table. Okay, so this is also a reaction that occurs in stars. It's how they emit light. They undergo constantly nuclear fusion, fusing helium. In this particular example is fusing it with nitrogen, but for the sun, it's helium and hydrogen. Okay. So for this particular example, it's helium and nitrogen that are being fused together to create an oxygen atom. Now, when those nuclei fuse, it's basically releasing a whole bunch of energy also from that nucleus. So this releases a huge amount of energy. Huge amount, and forms a larger, heavier nucleus. And in this case, for this particular reaction, it's creating oxygen. So they join to form a heavier, meaning more protons and neutrons inside the nucleus. Okay. The products of a nuclear fusion reaction are not actually radioactive. So it's a better option for harvesting energy for ourselves in a nuclear power plant. However, there's no commercial fusion reactors being used right now or under construction because it's a question of how to contain the reaction, and because it requires nuclear fission to start this reaction, there's a lot of radioactive fallout. So even though the actual fusion reaction is not radioactive, it's still a part of something that creates radioactive byproduct, which of course is very dangerous. I'd love it if we all turned into Spider-Man or other superheroes, but that's just not the case. We're actually going to be watching a video of what happens when we're exposed to radioactive materials later. Okay. So the other form of nuclear reaction is fission. So fusion is fusing together. Fission is breaking apart. So this occurs when a high-speed neutron basically rams into an unstable nucleus and causes it to break apart. Okay, so the neutron bombards it, becomes unstable, or it was already really large and unstable, and it breaks apart. So these happen with heavyweight nuclei, so ones that have lots and lots of protons and neutrons inside the nucleus. They must be larger than iron. Iron seems to be that cutoff period or cutoff mass. And this is used in modern day nuclear weapons. It's also used by countries, including Canada, to generate electrical power. So even though it's a nuclear reaction, it creates electrical power at the end. The biggest one we have is in Ontario. It's the CANDU reactor, which we will talk about actually in our next lesson. So this one must be heavier than iron. You have a high-speed neutron. So something has caused this neutron to blast out. It's usually a part of some sort of decay model, or something else happened, like an explosion. And it's going to ram into the nucleus of that uranium atom that we see here in our diagram. So when it becomes unstable, it's so unstable that and it's so large that it ends up splitting apart into two smaller atoms. And in this case, it's krypton and barium. Okay, so it's unstable, so it splits into two smaller nuclei, just the plural form of nucleuses or nucleus. So the daughter products, so we call these the daughter products. And we call these the parent products, or parent, not products, parent reactants is the uranium. And then the daughter atoms are the two that I have indicated on the diagram, and they're often radioactive. Okay, so these are often radioactive. And it causes a waste radioactive problem. As anyone who's watched the Chernobyl documentary or a Chernobyl series on Netflix, or the Chernobyl documentary that we actually will be watching in this course as well, that waste problem, if you cannot contain it, if it comes out into the population, it has catastrophic results, especially for those directly exposed to it. So there's a radioactive waste problem, and currently we don't really have anything that we do with the waste. We just bury it and contain it. There was an article that came out about lasering, the potential to laser waste material, like nuclear waste material, to a harmless state. So going from harmful to harmless. But I think it's still in its testing stage, and I'm hopeful that they can figure something out for that, because there's only so long we can continue harnessing nuclear fission reactions for energy without having to run out of space and options for containing the waste materials. So this reaction, the whole reason we use it is it releases a whole bunch of energy. When the nucleus splits. Okay. So that's the difference between nuclear fission and nuclear fusion. They're both nuclear reactions that create and release an abundance of energy. They both have issues with containing the energy and also with waste products, waste management products. The one time you don't really care about containing the energy is when you're talking about weapons, because of course when you design a weapon, you're talking about damage. So the containing the damage of the explosion or the reaction is not a factor necessarily. And so what we're going to do now is we're going to watch a video about nuclear weapons. All right, I hope this was helpful to you guys. I hope you enjoyed it. If you have any questions, please let me know.